Here's a related rate problem that I'm going to do two ways. Several students struggle with implicit differentiation, so there are two ways that you can do a lot of these problems. If you want to think about it in a different way. So in this case, we have a baseball diamond, and that's a 90-foot square. That means on each side of the diamond, it has a length of 90 feet. So like this, 90 feet, etc. all the way around. And so since it's a square, each of these corners is a right angle. A batter hits a ball along the third baseline and runs to first base. At what rate is the distance between the ball and first base changing when the ball is halfway to third base, if at that instant the ball is traveling 100 feet per second? This is kind of written a little awkwardly, but it's not impossible to do. So the idea here is the batter's running towards first, and the ball was hit along this baseline right here. Okay, so the ball's traveling along here, and they're talking about at what rate. So that's the question we're trying to answer here. At what rate is the distance between the ball and first base changing? So here's where the ball is, and there's a distance between the ball and first base. So what we're trying to find, what we want to find, is the distance the ball is changing with respect to time. That's what we want. At what rate is the distance between the ball and first base changing? So this is a rate. That's the distance between the ball and the first base. That's what we want. So if I continue with what I'm given, it says, well, when the ball is halfway, so the ball is, when ball is halfway, this is what I'm given. I'm going to call that distance x because I don't know what it is. So I'm going to find d dt when x is 45, or at the moment when x is 45, and dx dt is 100 feet per second. How do I know that that's dx dt? If at that instant the ball, that's the ball, is traveling 100 feet per second. 100 feet per second. This is 45 feet. Everything here is in feet. Okay? When doing the next step of the problem, you do have to relate those two things together because that's all the information I have. I have dx dt, that's given, and I have d dt, which is what I want. So when I look at the picture, I see that they're arranged in a right triangle. So I can say that d squared is equal to x squared plus 90 squared. That's terrific. From here, I should be able to work through the problem. Now, if I want d dt, I have to somehow use dx dt alongside that and this equation to relate the rates together to come up with my solution. So the new method, or the method that doesn't use implicit differentiation, I'll call it method 1. Method 1 actually uses something called the chain rule. Now, it depends on your instructor if you know what the chain rule is, but you can actually relate rates together to understand how the chain rule works. So in this case, I have dd dt, and I have dx dt. And if I use the chain rule, I know that dd dx times, I'm sorry, that should be an x. dd dx times dx dt is going to give me dd dt. So the idea here is these dx's will cancel. So I take the ones that I'm given and I create a rate that relates the three together. So again, given dx dt, given d dt, that what I want, I know that if I multiply dx dt times d dx, then I get the rate that I want in the end. So let's see, since d dt is the thing that I want to find, I need to come up with the derivative of d with respect to x, and I have to come up with dx dt. dx dt, though, is already given to me, so I just put that in there. So I need to come up with dx. So I know that d squared is equal to x squared plus 90 squared. I also know that d is equal to the square root of x squared plus 90 squared. And I'm only going to look at the positive root there since everything's distance. Now if I want to calculate dx, I just take the regular derivative like I would in earlier chapters. So let's see, that's like saying that it's x squared plus 90 squared to the 1/2. So I'm taking the derivative, bring down the power, subtract 1 from the power. The inside stays the same, and I multiply times the derivative of the inside. That's the chain rule. To simplify that, I get the 2's go away, x in the numerator, and this whole guy in the denominator. X squared plus 90 squared to the 1/2. Now, even though those are both squared, I can't take the square root because they're connected by a plus sign, so you have to leave it like that. Over here in my formula, though, I can replace dx with that guy, and then I'm not going to put the number in for dx dt for another step, so just hang on. So I can replace that with x divided by x squared plus 90 squared to the 1/2 times dx dt. Now here it says we're supposed to find that number when x is 45 and dx dt is 100. So now at this point, since everything's in terms of x's, I'm going to put that information in here and see what I get out. So let's see, if I put x equal 45 divided by 45 squared plus 90 squared to the 1/2 times 100. If I put that number in my calculator, so 45 times 100 divided by 45 squared plus 90 squared, all raised to the 1/2. Make sure I have that right. And I get 44.7214. 44.7214. And what's my unit of measure? Well, d is measured in feet and time is measured in seconds, so this is going to be feet per second. Now I'm going to do this method again, or do this problem again using method 2 and see if we come up with the same answer. Now method 2 is using implicit differentiation, which is a standard for related rates. So method 2, let's see, I have d squared equals x squared plus 90 squared, and I'm trying to find the derivative of that distance with respect to time. So the implicit differentiation says, well, if I want something with respect to time here, I have to take the derivative of everything with respect to time. So that means I take the derivative with respect to time of the left-hand side, and I take the derivative with respect to time of the right-hand side. Using implicit differentiation, I take the derivative of this guy as if these letters matched, and then I realize the independent and dependent variables aren't the same, so I have to add my dt. Again, that's a form of the chain rule. Derivative of the outside, evaluated at the inside, times the derivative of the inside. Oh, here, I take the derivative of x squared in the same way, dx dt, and the derivative with respect to t of 90 squared is 0, because 90 is a constant. So in the process of solving for d dt, I come up with d dt is equal to 2x times dx dt divided by 2d. 2's go away, so I'm left with x times dx dt divided by d. At this point, I know that x equals 45. I know dx dt is equal to 100. And I know that d is equal to the square root of x squared plus 90 squared. Found that in the previous problem. So here's d. If I just solve for d, I get square root of x squared plus 90 squared. And again, I'm using the positive root because I'm talking about distance here. If I plug all that in, including the fact that x is 45 here, I get 45 times 100 divided by 45 squared plus 90 squared to the 1/2. And if you take a look and compare, let's see if I can get it all on one screen. I may not be able to. Look at that. 45 times 100 over 45 squared plus 90 squared to the 1/2. There it is. Same thing. So I know that this is approximately equal to 47.7214 feet per second. And I don't know, let's listen to your instructor. If they say to use implicit differentiation, then use it. If they don't specify and you understand how these three rates relate in this manner using the chain rule, this is not a bad method either. They are a little different in how you solve them. If you're really good at implicit differentiation, this seems a little straightforward, but again, it just depends on who you are. It depends on your instructor. So just listen, pay attention, and choose which one works best.